I will wait just 2 minutes and then maybe we will start. Okay, I think it is time to start. I'm very sorry for the technical problems that happened to happen just now. Seems like they are originated from Microsoft and from Teams, but glad that almost everyone at least could join the WebEx, and I think we could start now. So my name is Veli-Pekka Salo. I'm working as a team leader in the Vapais in the IoT and communication solutions. Today we will talk about some of the industrial IoT protocols, industrial IoT in general, and also the ERP, the enterprise resource planning, and some let's say mega trends concerning those items. Shortly about Vapais and myself. So I've been working for Vapais almost 10 years and over 20 years in different kind of software projects. And yeah, let's say IoT communication technologies and such, they are very close to me, and I enjoy working those. Vapais, on the other half, we are a Finnish software and AI, artificial intelligence company. Our headquarters is in Vaasa, which is the, let's say, the energy capital in the Nordic region. So there are, let's say, big energy companies in this area like ABB, Wärtsilä, so on. And from those perspective, there is a lot of IoT and also industrial technology focused to this area. Vapais is, like I said, it's a software company, privately owned. There are some 350 industrial IoT and AI experts, and we are in 10 office locations in Finland. Just to give some background to me and the company where I come from. Today the agenda, so we will talking about generally about Industry 4.0, let's say IoT, enterprise resource planning, and so. Then we will focus more on the factory floor communications and also OPC UA, which is one of the most promising, let's say, emerging communication technologies in the Industry 4.0. And then we will have one use case example how that showcases the digital transformation in energy production and how OPC UA helped in that. And I encourage everyone, please, you can interrupt me at any point and ask questions. I won't be following the chat. At least now I can't see it, but you can, if you have questions, just stop me and ask the question, and I can then go more into detail in that. Okay, good. So to give some background for the Industry 4.0, so what does it mean, and what is the big picture that we will be focusing today? So if we think about what is happening today, so cyber physical systems are getting more and more common in the industry. So this actually started back in the 1800s. It started as a first industrial revolution, which was basically the mechanization, and when the steam power was invested and water power was basically figured out. And that was followed up by the second industrial revolution, which was basically the mass production. So assembly lines and electricity became common, and those were used in the production. And then computerization and automation was the, let's say, the third industrial revolution. So then everything was automated, and computers became to help the industrial manufacturing. But now as we see around us, there's basically a tremendous change in the communications, like how people communicate with each other. There are mobile phones and everything like internet and things like that. They can be in many ways used for communicating with each other. But that all is just now starting to happen in the industry also. So cyber physical systems, wireless communications, new communication technologies, those are just gaining ground in the industrial systems, in manufacturing and in let's say in all business sectors like energy production, manufacturing, and so. And there are some let's say bigger trends there, like bigger let's say concepts, important concepts. And one is that machines and things in the industrial systems, they are getting more and more smarter, and smart connected things that gather basically information from the processes, they are getting more and more common. There's big data and analytics are collected more and more. Cloud computing is becoming a norm. Then cybersecurity is one of the key important things, how to keep the information that is collected, how to keep it safe. Then robotics, it's not anymore computerized, but it's also autonomous. So programmed things become self-learning. They start to do things themselves, or they start to follow programs that allow learning and artificial intelligence. There's simulation and digital twins, so we are able to do better and better models of the processes. And machine vision is also helping the industrial system. So it's possible to augment autonomous things using the machine vision. So those are basically the things that are gaining ground now. And as a general trend, there is a aim to improve the flexibility and versatility and usability in the smart factories of the future. And traditionally, we have had this kind of, let's put the pointer into a laser. So traditionally, we have had this kind of communication pyramid, where basically we have near the devices, we have a I/O layer, then we have the PLC layer and SCADA layer, and so. So this is transforming into a more heuristical communication system, where almost everything is communicating with each other, and not anymore like from layer to layer. And let's say the 5G and other emerging industrial standards, they focus on this machine type communication and then on the industrial Internet of Things. And if we think it from a bit different point of view. We basically how things are evolving. We used to have a connected things in phase one, where we monitor things and visualize data and so on. And now we have more and more. We have predictive, so we are not anymore monitoring things, but using the data. We have the advanced analytics and models and machine learning. We are predicting what will happen in the future. And the next step then is this cognitive level. So this will use the prediction to do basically automation, and we will have the digital feedback loop. So data will be used to create new services and automation. And machines can basically do automatically things. There is some examples, for example, from the energy management point of view, how these will go. So in the connected phase, we will have basically information is used for the energy usage and optimization and building energy management. And in the predictive phase, we start kind of use the data for predicting that how much it will be used in the future and how it can be optimized and how the let's say the building and infra management can be optimized. And in the cognitive phase, we will use this energy trading. So we will basically participate in the energy market and use the information collected to predict that how much energy is needed in the future, and we can in the real time use this information for energy trading, for example. A little bit more about this automation pyramid. So what basically is the, let's say in the factories, the information systems, how they are connected to each other. So this is used to represent the different layers that traditionally has been in the industrial systems. So near the field level, we have the sensors and control machines. In the SCADA level, we basically have the visualization and we have where we basically gather together the information in the machine level. And then in the enterprise level, we have basically information from for example, from multiple factories. And then there's this amount of data and number of components and time constraints. So nearer the machines we are, the faster is the data communications needed. And also the number of components is higher there. Whereas if we go higher and higher in the automation pyramid, then the amount of the data increases, but on the other hand, the number of the components decreases. And same time also the requirement for the data transfer goes lower. So we have a real-time communication lower in the automation pyramid and non-real-time communication higher in the pyramid. And MES and ERP, those are the terms that are quite often used here. So MES simply means manufacturing execution system. And this is basically, for example, in one factory or in a single plant, where in this layer we have basically the manufacturing process which is taken care. So this is this MES execution system which takes care in a single plant level. And ERP is then on the enterprise level. So for example, the whole corporate level decision making. In the big picture, again, what are the IoT and ERP needs? So there are some trends again. So need is of course to collect KPI information from the manufacturing and field devices. And at the moment, IoT is only supplementing the other information sources. But trending is that more and more IoT information would be used for the analytics and business intelligence. And in future, the target is of course that we would use the IoT data to help creating new services and processes. And here is actually a big picture of the ERP, so enterprise resource planning. So it means the whole like everything from supply chain management, manufacturing, project management, customer relationships and sales, services, human resources, and finance. And there are different things that IoT data can help there. For example, in the manufacturing phase, we could have IoT data collecting information how the manufacturing process runs. So, for example, the used statistics and such. Or in case of failures, we can get real-time information, how much failures we, for example, have and so on. So IoT can help there. In this today's presentation, I will actually focus a little bit more on the field level communication protocols and what happens in the factory floor. And I collected some statistics here that what kind of protocols and communication methods are used at the moment. And here is kind of really good presentation that the industrial Ethernet protocols, they are gaining more and more ground in the factory floor. There is, for example, Ethernet IP, Profinet. They are getting more and more ground. And then the traditional field bus protocols, they are getting less and less. And also the wireless methods, they are getting higher and higher. And there is quite many different protocols at the moment in the factories used. There's Profibus, Modbus, Profinet, Modbus TCP, PowerLink, so on. Depending on a little bit. In the Europe, a little bit different protocols are used compared to the USA. But for example, if we take a look at the Modbus, so this is very traditional communication protocol in factory floor. This is basically enables connecting a master, for example, a PC and some several slaves, for example, measurement and control systems. And it has basically a manufacturer independent data structure. And then it has a TCP, so for the Ethernet communication, and RTU, which is then a serial communication, and ASCII protocol, which is used a little bit less. And it's actually this kind of server-client communication protocol, where client is basically the active part. It makes a request, and server then responds with the response message. And this is basically let's say, very standard method of communicating in traditional communication protocols. Here's the function codes, which then basically are like a keywords that what the protocol wants to achieve. So there's, for example, read holding registers. So this would go in the protocol message. The client would send a read holding register request, and then server would respond with the read response, which would contain the data, and write holding registers, and same way that would contain the request and then the data, and server would then fulfill the request and then respond that okay, data written. This is quite common kind of communication method. But then there's a lot of, let's say, challenges in the today's communication methods. So basically the communication protocols, they are vendor specific and designed for specific industry in mind. Implementations and ecosystems, they vary. And also the umbrella organization may be financed by single players. There's not so much interoperability, and also the cybersecurity might be poor. For example, this Modbus, it doesn't have at all cybersecurity. And then it's missing systematic way of modeling data, systems, machines, and entire plants. And it might be really hard to connect IT systems and cloud. So they are really designed like machine-to-machine communication protocols. And on the other hand, the requirements would be that we would need to have a interoperability. So basically, if we want to achieve the industry 4.0, like things are more and more communicating with each other, we of course need interoperability. Scalability. So we might have different kind of systems that communicate with each other. There might be small IoT devices, whereas in the factory floor, there might be large SCADA systems, and they all need to have a same communication protocol available. We need data and information modeling, like we need to describe the systems and messages that we want to exchange with each other. Has to be standardized. So of course, like agreed with the big players that, okay, this is the communication protocol we need and has to be standardized, has to be reliable and robust, and also security has to be inbuilt. And this Industry 4.0, it actually started as a German initiative, Industry 4.0. And in this initiative, the OPC UA is the only approved communication layer standard. And next I will talk a little bit more how the OPC UA will help in the industry, achieving the requirements of the Industry 4.0, and how does it suit in the factories of the future. Is there any questions so far? Okay. Just I want to remind that if you have any questions, please just shoot. OPC actually started from the predecessor of the OPC. It was the OPC, Open Platform Communication Standard, which was Microsoft based and widely used in the process and manufacturing automation before UA. And then big players founded what is now called OPC Foundation, and it basically unifies the OPC standard, the old OPC standard, OPC-DA, OPC HDA, OPC AE, alarms and events standard, and it became like a de facto standard in the industry. And let's actually look at a short. Let's see how I change my. How do I change my pointer now? Just a moment. I want to click the video. Now I am a little bit unsure if I can use the audio also. But let's see.
Yeah, the audio is not coming through, Veli-Pekka.
So is it so that the sound is now not available?
Yeah, it seems so.
Yeah, okay. I'm not sure if in WebEx is possible to include the audio. But let's quickly go. I will
Yes,
then.
it is possible, but you can also share the link so it will be saved on a chat, so it can be accessed later on.
Yeah, let's see. Okay, I can also copy.
Or you don't have to put it in a chat because it's already in your slides.
Okay, let's keep it there. And let's continue from here.
Is the slides available later to this all material?
Yes, they will be available.
Okay, well, thanks.
Okay, I will stop it for a moment and basically explain a little bit. So OPC UA became then basically a unified architecture, which is basically platform independent communication technology. It's basically scalable also, so you can use it for machine-to-machine communication. You can use it for small IoT devices. It's for different platforms, like I already mentioned. Then it's security inbuilt, and also like mobile devices can use it.
How much there is open source code in those? There is a Linux.
Yeah, there is actually in the
Yes.
GitHub available the OPC UA source
Okay.
code. So
Yes.
you can find what is called OPC Foundation source code for C and C++, Java, and C#.
Yes.
You can find those in the GitHub. And then there are also some open source codes, like I can then basically include also in the slide set some open source references.
Okay, and the OPC itself is an open source also, the Microsoft version.
Yeah, the old OPC protocol is not used anymore so much.
Okay.
So that is more and more being replaced by the OPC UA.
Okay.
But also the specification is also open source, so you can access that free.
Yep.
Okay, so OPC Foundation, that is basically nowadays it's quite large ecosystem also with almost 800 members. And as we can see, there are some really big players like ABB, Intel, KUKA, Robotics, and let's look what else we can figure out. Samsung, Siemens, so big industrial players from everywhere in the world. And a starting point how to get started with the OPC UA code and OPC UA is you can click and go to the OPC Foundation web pages, and you can find different kind of resources from there. There's a specification available, samples and tools, presentations, discussion forums, and so on, newsletters, case studies. And then if you do more and more, and then finally you might have a OPC UA product of your own, there's also a certification and test tools available. And then let's say the evolution of the OPC UA is taking care in the working groups. So if you are OPC Foundation member, then it's of course possible to participate also at the working group work. And one of the big powers in the OPC UA is the consistent information model. So it's basically possible to express complex things and with each other, and it's also suitable from machine to machine to cloud. And let's say there's some examples, so it's very suitable for the IT layer, so you can make vertical communication, cloud integration, you can use it for the remote access, then it's very suitable for the controller to controller or control to field device communication. There's even a roadmap for the 5G and wireless communications here, so it's very, very future ready also. Here is a small example of the information model in the OPC UA. So basically, if we would have in a very simple example, so we would have a reservation. So there would be some, let's say, variables that express things. So for the reservation, it would have two variables, when, which would say that end time and start time, and who made the reservation. So last name, first name, for example. And then there would be a method, for example, for cancel. So similarly, the OPC UA expresses these kind of things. So you can describe the reservation using a base object in the OPC UA. And then the reservation would have a reference to, or the who made the reservation would have a reference to this. So person would be the one who made the reservation. And then you would be able to express same kind of things, that who made the reservation when, and also you would have methods available and different kind of relationships. So this allows the very complex things to be expressed in the OPC UA. And here is actually one example of this semantics of this communication protocol. So there is a companion specification for the robotics, and a robot would have a different kind of axis, for example, for movement. So there would be information like what kind of robot it is, what kind of movements it allows, and so on. And this all would be possible to describe with the OPC UA. So you would have information that what kind of motion device it is, what kind of safety states there are, what kind of controller states there are. And this would allow interoperability, because if you fulfill this kind of companion specification, then the other party which is communicating with the robot, it would already know what kind of information is going to come from the robotics or from the robot. And this allows basically that different manufacturers, they are able to create robots that are able to communicate, plug and play with each other. Okay, companion specification, not only robotics, but they are for different kind of purposes. There are different business domains that allow companion specifications. For engineering, like devices there's companion specifications being prepared for the devices, for the energy sector, for the factory automation. And these basically they are then let's say they are building information models on top of the OPC UA specification, and make things compatible with each other in different business domains. And this will be a really, really nice achievement, actually. Okay, how to start? There was a little bit already about the OPC Foundation web pages. There's actually the tools and code examples you can find from the GitHub. This actually answers your question. There's the open source software available, there's certification available, and so on. And thousands and thousands of examples can be found already. Let's see how we are doing schedule-wise. I have a little bit more deeper presentation about the specification. So OPC UA basically, the specification is divided into different parts. So there's basically the core specification part, which describes the basic core things like overall concepts, security model, address space model, and so on. Then we have the access type specification, which describes, for example, the data access and historical access, how the alarms and events, how they work in the OPC UA. And then the utility specification describes basically the discovery and aggregate features. I could actually jump over these. Well, some simple examples of these. So what does the data access mean? So basically in the OPC communication, we would have a server, OPC UA server, and OPC UA client. And then the OPC UA server then exposes the real life objects. These would be, let's say it could be some kind of gateway device that provides measurements from the sensors. So then it would provide like a root folder, some folder collecting things, and then the gateway object. Under that, we would have the sensor measurements. And it would allow the OPC UA client to connect to the server and then read values directly or subscribe to the changes of the values. And then the server would provide the data. So this is simply the data access model. Historical access would only mean that then our server would have possibility to store historical data. So it would have a database or similar system that collects data. And then our client would be able to connect the server and then ask data, for example, from the current day. Give me data values for this item for the current day, for example. Events, those are also supported in the OPC UA. So there would be for example, describes different kind of events that happen in the address space here in the OPC UA server. For example, we could have a new sensor added to the system here. So this would then in turn, this would in the OPC UA server, this would be added into the address space. So now we have a new measurement point here, which is a distance. We added the distance sensor and we have a new item here. So measurement point distance added here. Okay, we would be able to inform the clients that, okay, there's a address space has changed. We have a new item here. So we would trigger model change event. And then the clients would be able to know that, okay, now I need to browse the address space again to get up-to-date data. Alarms are a little bit similar. They are basically events that have a state. So for example, now we have this newly added distance sensor. What happens if the measured distance is too short? We create an alarm. An alarm is a state that stays on as long as the distance is too short, for example, or too long. And then the client would be aware of this. This could be, for example, some kind of let's say application that is reading the values from the factory flow system. And then in the factory flow, something is causing the alarm and informing the users here. So users would be able to also to acknowledge that, okay, I know this is because I positioned the device a little bit too close also. So he's able to acknowledge the alarm. But this, if you compare this to a let's say, traditional communication method. The OPC UA gives so much more possibilities to exchange information. There's even methods available. So OPC UA clients can call small functions in the server. And these would, in the server, they could cause some action to be done. Some system concepts. So client server model, as already a little bit described here. So real objects are basically mapped into let's again take the pointer. So real life objects, they are mapped into what is called an address space. So we have a machine or something we want to describe as a measurement points or nodes. And these nodes we then express in the OPC UA server API. And these nodes are then shown to the OPC UA clients. And then clients, they create a session to the server and they read data points or they subscribe to the changes. This is also subscription is like it's like registering to the, let's say, registering to a newsletter, and then the server provides the information only when there's something to inform that, okay, now the data has changed, and it will create a event that causes client to be informed. And this is actually a great way to basically balance the communication budget. So data is not, there's not, let's say, data is moved only when needed. So this basically automatically creates a communication model where only when needed data is moved. Goes quite deep already. There's attributes, references, and variables. Attributes, I will actually shortly give a short example of these, but when I talked about the measurement points or nodes, then there are different attributes that are attached to these. So there's, for example, a name, description, data type, status, and so on. So they basically, for example, the status information is really important in the OPC UA. So you know basically if the value that you get from the server, if it is good or not, if you can trust the value. You get the data type and also description. You could have references to different kind of objects. So this gives a possibility to describe very complex objects also. Variables, you have different kind of variables available. You can have properties or data variables and so on. Some concepts here. Session is what happens when the client connects and connects to the server. There's certificate validation and user authentication happens there. Browse is when the client requests the address space from the server. And subscribe is then when you subscribe to get the data changes and events. This I think I will skip. Goes quite deep in the protocol. I think we could have a short demo actually. So take a look at how the server and client communication looks. I will use unified automation tools for this. I have a small demo server and then a client I will use. So if I just start typing UA CPP server, this would start a simple OPC UA server with some demo items. And then I will start a client. And I happen to have everything pre-configured, so I can just click on the connect. And actually, let's take a look at what's here in the parameters. So for the connect, we would need to know the server endpoint address. And then we have some security settings that we will have a deeper look shortly. But I have just configured that there's no security at all, and also the authentication is anonymous. But now I can simply connect, and I see that I will have the address space here in the left. So this is basically the address space that exposes the real life objects. So I would have a root object, then collecting object folders, and some folder that contains some building automation stuff. And okay, I would have a simulation of air conditioners here. So using the client, I would be able to register to read the humidity value, for example, power consumption, and temperature. So now the server is providing me the data when it changes in the server. Then if we click on the temperature, for example, we can see these attributes. So in the address space, all items, they are identified by a node ID, which is basically unique. We have the value, we have the data type, we have a user access level, and so on. So these are the attributes that each node has. And for example, the value that has a status code good. Then we could have a history trend. This is actually, I think, not providing some history, but same way we could actually register to listen for the events. So I can just drag and drop the server node here, and it will start listening for the events. And let's see actually what happens if this air conditioner, if we call this stop method, and we could stop it. And okay, we get an alarm. So we get an alarm that this air conditioner is now down. It's actually alarm is active. It says it that way. And we could also acknowledge that, okay, this is down because I manually turned it off. Service. I could be, for example, a service manager in some factory. So I can acknowledge the alarm, and it could go into some kind of backend system that then stores the information that, okay, this is not a serious situation because it was acknowledged already. And if we start again, I see that the alarm situation goes off. So very simple example how the OPC UA server and OPC UA client communicate with each other, and how the address space looks, and how, for example, the alarms and events work. Let's go back to the topic. Security model. This is actually very important in the OPC because it has the security inbuilt in the protocol itself. So there are some objectives in the security. So first of all, there has to be authentication. So applications have to be authenticated. For example, on client and server and users should prove the identity. Then there has to be the authorization. So different kind of access has to be allowed or denied. So someone could have a read access, whereas someone else, for example, a manager profile, would have a read and write and execute access. So different kind of authorization levels. Then there has to be confidentiality. So data has to be protected. So data has to be encrypted and secured. And it has to be in integrity in the system. So receivers, they should receive the same data that was originally sent. And auditability, quite often there's a concept like audit trails. So afterwards, you should see that who has done and what. So for example, user activity has to be recorded and saved somewhere. So logging has to be easy. And then availability simply means that always the services operation should be ensured. And for example, different kind of flooding attacks or IP attacks are not possible. And in OPC, there's a 3-layer security architecture. So applications are secured. There's a certificate authentication that secures the applications, and there has to be a certificate handshake. And then there's the user authentication, so user level authentication, and that is taken care most often using the username and password, but could also be by the certificates. And then there's this let's say communication layer security. So there's confidentiality, integrity, and application authentication. So there's basically an encryption of the data. So 3 layers of security in a protocol. So security policies, there's a security policy basically in OPC that specifies what kind of security mechanism are used in the protocol, what kind of algorithms, and how the server basically then maintains the security policies. User authentication and authorization and application authentication. And here is actually quite nice example of how the certificates. So certificates are basically, they are a public and private key pair. So in OPC UA, it has a, for example, server has a private key and public key. That's how the certificates usually work. So this private key is used for encrypting the data. And then the client who reads the data from the server, it has to be able to decrypt the data. So this means that the server's public key must be given for the client. And once the server then exposes data to the client, then the data that is encrypted using the private key, this is decrypted using the public key, and vice versa. So this is basically the manual certificate handling that is happening in the OPC UA protocol. So each other there's a certificate handshake. And now this basically prevents that, for example, if there's a if there is someone who wants to, for example, happens to have access to some OPC UA application, and he could even steal the username and password and try to connect to the server. But since server doesn't have the client's public key, and also the client doesn't have the server's public key, then the applications would not be accepted to connect. So this is very effective way to secure the communication. Then, but we can immediately see that there is probably some problems in this. So what if there are many clients that each try to connect to the UA server? So we would need to get all the public keys in the server certificate store and vice versa to give the server public key to all clients. So that is not very effective. So then we have a CA signed certificates. And this is a little bit like a let's say police department that provides you a passport. So there's a public authority that gives a certificate that states identifies you, gives you a passport, for example. And when you see someone else's passport, you know that okay, this is given by a trusted party. So I can trust that this is a valid and I can trust this person. Same way, this kind of CA certificate authority signed certificates. So if I have a certificate that is signed by some author, then I know that I can trust this certificate. And this actually can make certificate handling a lot easier in many situations. Okay, quite complex things but let's go a little bit deeper still. Quite often, if we think about modern communication methods, then we already covered. We have security. We have a lot of means to make the communication reliable. But what if the network itself breaks? Then that would of course break the communication. We can actually avoid that by having redundant systems. And redundancy is also inbuilt in the OPC UA. So we have transparent redundancy and non-transparent redundancy. And transparent is something that is not visible for the OPC UA endpoints at all. There's actually two servers that are behind the scans. Client doesn't know at all that, okay, now I'm communicating with two servers. But it's also possible to have a non-transparent redundancy. So then client would have a server 1 that it is connecting, and then this would have, for example, this kind of hot redundant server that is able to immediately provide the same data as the backup server, and vice versa. The backup server is immediately able to provide same data as the server 1. So we can actually create systems that use different networks. What if we make the communication from client to server 1 using the different network, and from client to server 2 using a different network? We would actually have a really reliable system. So if one of the networks breaks, the client is immediately able to connect to server 2. And this would actually also make it possible. We could make what if we need to update the softwares into server 2, for example? We can just shut it down, update the software, and clients are happily communicating with the server 1. And once updated, we start the server 2 and then shut down the server 1 and start updating there. And no one knows that softwares are being updated. We can keep the services on all the time.
So it's rating, the server 1 is on and server 2 is a backup one always.
Yes, it's possible. Yeah, it's vice versa also, and they can be actually online all the time.
Yes. Okay,
Yeah.
similar than normal web. If you have switches and that kind of things, server halls and those.
Yes.
For normal web. Yes.
Yeah, it's a
works.
little bit similar concept.
Okay. Yep.
But basically in the protocol level, the support for this is done. So you don't need any programming to achieve this. If you make the client software, it's already baked in the protocol level.
Okay.
I will skip over again basically the failover models. What is basically something that is always on. So failover is if you fail over from one server to other server, then it's all the time available the other server. So you have different kind of failover models, but I think I will not go very deeply into these now. Yeah, there's also basically like already a little bit explained the network redundancy, but you can have this basically baked in the OPCUA and OPCUA supporting from the scratch this kind of features. Historical data I will go really quickly through. So this is basically only something like time series data. You have possibility to read time series data, but you could also, if the server only supports it, you could also make scenarios where you have possibility to update the time series in the server or even delete some values. So those are basically supported by the OPCUA. You have different kind of query parameters you use to access the data, start time, end time, and how much the data to read, and so on. Alarms and events, we already see this in action a little bit, but alarms are basically a state of or a condition of some sort. So server will depending on what actually happens in the real life objects. So it exposes those objects in the address space, and there could be some kind of event like a sensor reacting or giving a reading that okay, now something is not right. So that will create an alarm. An alarm is then registered by the clients. And for the alarms, you can acknowledge those. But on the other hand, if you think about what kind of things usually could happen in the factory, so if normally things are running just fine there, usually you produce what you produce and things are running fine. But then when something starts to go wrong, then you would probably have a lot of information quickly coming to you. So there would be a lot of alarms coming and a lot of information from different kind of systems. And it's important that you could also shelve some alarms. So you could basically, when you start getting data, now something is wrong, you start to sort it out a little bit like, okay, this is not important information. I can decide that this is not something I need to know now. I can shelve it. So I just put it, like acknowledge that, okay, don't care about this anymore. And then I can focus on more important alarms that I want to get information. That actually helps pinpointing the problem in the event source, that what actually went wrong and what is the root cause. So in a sense, OPCUA also supports problem solving by giving different kind of ways to interact with the alarms and events. Some future trends. So of course, OPCUA is evolving all the time also, and if you are aware with some modern communication protocols like MQTT or AMQP, you might already think that okay, this kind of client server model, it doesn't work in all scenarios. So, for example, in web activities, so if you are connecting things with cloud systems, for example, so what is typical for the cloud systems? You don't know necessarily how long things will take there, how quickly they react. So you need to have an asynchronous workflow. So you don't have possibility to wait for the response immediately. Instead, you send some information and then you register to receive a notification then later on. It's like a promise that whatever you send, the system will give you a promise that, okay, I will try to do this now, and I promise to get back to you when I'm done. And this is the asynchronous model or asynchronous workflow. So you have you have to have possibility to wait for or not wait for the event, but to get it when it's done. And also, if we have a lot of resources connected, for example, let's say we have IoT sensors. So what if we have hundreds of sensors in the system? It's impossible to use this client server model in large scenarios. And also in the, let's say in the deepest levels of the factory floor, we need really low power and low latency systems. If we think about this client server model, there's always first there's this connection phase, like creating a session and handshaking, and then you are able to start the information flow. So that doesn't work very fast. So instead you have to be able to just send the information very quickly, and then anyone who is interested about it should then receive it. There shouldn't be any like activities that has to be done before you are able to send the information. So there's actually a PUB substandard in OPC UA, publish subscribe pattern, and that enables one-to-many and many-to-many communications. So you can send messages between each other when they decide and not when requested. And it allows distributing this information efficiently. And in OPC UA, there's two types of communication. Let's say two types of communication. There's brokerless communication, which uses the network infrastructure to send the information, and then broker-based communication, which uses a broker for delivering the messages. And in this publish subscribe pattern, this is used by other protocols also, like MQTT also uses this. MQTT, on the other hand, only supports the broker-based publish subscribe, but the pattern works so that you have a publisher nodes that are the source of the information, and then they just send the information using different kind of topics. And topic could be, for example, a temperature. Let's see, do I have a better slide of this? That goes a bit too deep. And then the subscribers, they register to read the topics. For example, publishers here might be sending the temperature, and this subscriber here might be registering to read the temperature. So they just send the information, and then using the broker or the network infrastructure, the messages are delivered to the subscribers. So publishers, they have no idea if the data goes or if the publisher doesn't have a knowledge of the subscribers, it only sends the information, and then it's the responsibility of the subscribers to receive the data. And this is actually really nice method in the factory floor. You can use the network infrastructure, for example, the UDP communication, to very fast sending data. You just shoot it into the network and then deliver it everywhere in this network, and then the subscribers, they get it really fast. And broker based, then this is really nice for example, for the cloud communication. So we could send the data to the broker, and broker then delivers it forward. There is, like I said already, loose coupling of publisher and subscribe. They don't need to know about each other. And then what is really nice part in this, there can be these security mechanisms, same way as in the OPC UA. So there could be a separate security key server. So publishers and subscribers, they would each register first to the security gate server, and this would authenticate that, okay, this publisher is able to publish data to the system. And similarly for the subscribers, they each get their own key, and using the key, they are able to subscribe to receive the data. Another fast evolving, let's say, initiative in the OPC UA is the usage of the time-sensitive networks. So in the beginning of the course, we had a short introduction in the field bus communications. So at the moment, most of the very fast communications in the factories, they are using field buses, if we talk about the real-time communication. So real-time means that we have a timing, let's say we have a requirement to get the data within certain interval from sender to the receiver, and it has to be always guaranteed. And so far, OPC UA didn't fulfill this requirement. But TSN, or time-sensitive networks, this was initiated by the major players that, okay, instead of the field buses, we want to use this OPC UA because it's cross-platform, and it basically guarantees the interoperability. So we want to use this also for the real-time communication. And for that reason, the TSN initiative was started. And there are really big players who then started to back up this. And in the TSN, let's see if I have some examples. Okay, I'll talk instead. So in the TSN, basically the infrastructure is used together with the OPC UA. So you would have, for example, the switches and network infrastructure that would allow to have a clock synchronization. And using this clock synchronization, you then time the sending of the data and reception of the data, and then you achieve very low latency communication. And here are some examples with the application where you need this quality of service, or you have the quality of service requirements. So you could have in the factory floor, you could have a streaming data and events, some cyclic process data exchanges. You could have, for example, the machines communicating with each other. there would be the saw and press, for example, or robots would be communicating each other. And then what is interesting, there is also there is going to be a mapping between the 5G and OPC UA. So 5G guarantees this. What is the difference in the 5G and 4G, for example, is that 5G actually guarantees the ultra reliable low latency. So for this reason, 4G hasn't been used in the industrial systems very much, because there's no guarantee of the low latency. There is guarantee of the quality of the service, but not the low latency. But 5G will also guarantee the low latency. There's a guarantee that the data will go where it is supposed to go, and there is a guarantee that it will go as fast as promised. So that gives an option to use the 5G also for the industrial systems. You can have the robots discussing with each other, and you know that the data is going where it should be, and it goes as fast as promised. And there will be a mapping between the OPC UA and 5G, and this is actually really interesting scenario then. Yeah, so OPC UA TSN in a way also answers the challenges of the Industry 4.0. I think I'm still in time. I think we could then jump into the use case example. So one concrete use case example how we have helped our customers to succeed. Any questions so far about the OPC UA? If not, let's take another slideshow here. Originally, I gave this presentation in the OPC Day Finland 2020 last autumn, but we can use it as a use case example also in this context. We started cooperation with the Helen already 2014, and Helen is one of the largest energy companies in Finland, Helsinki Energy, and it later changed its name to Helen. It was founded 1909 and completely owned by the city of Helsinki, and some 500,000 customers throughout the Finland. And it actually Helen's district heating covers more than 90% of buildings in Helsinki. So Helen provides district heating and also electricity, and not only for those who live in Helsinki, but they also sell energy for the markets. And they have a quite strict target to be carbon neutral by 2035. And if we look at the Helen's energy production portfolio, they have a different kind of plants. They have a bigger power plants, for example, Salmisaari, Vuosaari. Then they have for example, Mankala water plant here, and they produce heat, electricity, and cooling in a very efficient process, where each is produced in a single process. So same time they are able to produce not only energy but also heat or cooling. And these bigger plants are then supplemented with smaller plants outside Helsinki or inside Helsinki. And there's an increasing amount of renewables like hydropower, heat pumps. There are really big industrial scale heat pumps that provide energy, and also solar power is increasing more and more. They have really large solar power plants available. If you compare Helsinki energy, Helen to the other big players in the world, they have really well performing processes, and for that purpose they basically got also award of world's best city energy. So usually the energy efficiency in the let's say capital area energy systems, they are in 60 to 70%, and Helen has much higher energy efficiency ratio, so they are doing energy in really good processes. What happens at the moment, or started to happen already years ago, is that the energy services is getting more and more digitalized. So trend is from these big energy plants into a smaller and decentralized production units. So we are getting, or they are getting energy from solar plants and heat pumps and so. So it becomes actually more and more challenging to manage and optimize the energy grid operations, and information becomes scattered. So information doesn't come from big systems where everything is aggregated together. It comes from here and there. On the other hand, there's a demand from the customers. So you need fast reactivity and personalized services. And transparency and predictability are needed in controlling the energy flows. So all this is not possible without digitalization, automation, and advanced analytics. And some challenges. So information systems, of course, if you have a multitude of plants, you don't source those from same supplier. So the energy production systems, they might be owned and administered by several different suppliers. It's expensive, vulnerable, and error prone to connect everything with vendor specific systems. So you need to have a simple and scalable secure connection between production units. And whatever you start to use for this, it must have a long-term support and roadmap. And OPC actually works really nice for this. So how you actually get cost savings with the OPC UA? You have a Industry 4.0 compatible solution, so vendor independent, scalable, you have security there, and you have the long-term roadmap. This actually gives the freedom of customization for the SCADA systems and information architectures. So you can actually, you don't need to care how the information system is designed inside a power plant or inside a heat pump. It can be any manufacturer's systems as long as it has the OPC UA interface and it talks OPC UA towards other systems. This actually gives clear responsibilities inside the Helen Corporation between different operators and systems and interfaces. Those who take care of the production plants, they only take care of the of their own responsibilities and take care that the OPC UA is available outside. And then where the data is collected, you can trust that, okay, everything can be connected using the OPC UA, and there's no need to understand what happens inside each power plant. And this gives a really simple architecture. It's easier to scale up and integrate with third-party systems, and it's actually easier to maintain and solve problems. Because whatever architecture you have, you eventually you will have some problems, but this will make it easier to solve those and easier to maintain. IoT Ticket is Vapis's IoT platform. We started to make already over 15 years ago, and it's actually complete Internet of Things suite and platform for building the applications. So it has everything from data acquisition to visualization and data storage. And you can easily create this kind of dashboards where you visualize the data. You can interact with the data using the flow programming tools, and you can create different kind of reports. And it's very straightforward also to integrate different kind of systems here. And we started creating the solution so that we chose the IoT Ticket as a backbone for the Helen solution. So we used the Enterprise Manager for visualizing then configuration solution. So for example, adding the OPC UA sites, adding the different kind of users, visualizing the data. There's a big data database for process data. So it stores basically the raw data from the power plants, and then the user and configuration information is stored in the relational database. I have soon coming a little bit better architecture picture here. And then we added the OPC UA modules. So Power Factory communication is done using the OPC UA clients. And the clients are basically responsible for connecting to each power plant. And then we can basically collect all the data and then provide it further. And actually C#.NET was used as a language and Windows system platform for the solution. At some points there was still the old OPC communication still used. So at some point we used this OPC DA to OPC UA wrapper or OPC UA to OPC DA proxy solutions, which basically work as a protocol converters. Here is actually a simplified architecture description of the communication solution. So we have basically a separate data for the process data. So raw values from the data points or from the factories are collected here. We have metadata, which is basically a user information configuration or so. And then we have the application layer where we are able to connect to the OPC UA sources and then providing the data further. And then there's different kind of activities possible to do. So for example, if you connect to the OPC UA sources, you would be in the administrator role. So you would add into the configuration OPC UA source address, security methods, and so. And you would add create the handshake between the source server and system client, which would be basically the certificate handshake. So make the applications to talk with each other, and then it would be actually plug and play to add the data points. So you would configure the endpoint URL, what nodes to add, and so on, and you can browse and subscribe to the events. And then in the factory, when the data changes, it automatically goes into the process database and is stored there. The interesting part actually comes in the data aggregation. So once you have connected all the power plants here, so then basically in the OPC UA server then provides the data forward. So this is now where we actually will have the enterprise level connected. So all the power plants are, or data from all the power plants is connected together. And then we have basically the, let's say the stakeholders or the information collected from power plants. So this OPC UA server then is able to provide the data forward. And this is then where the data can be used. So we get all the KPI information, how much the factories are producing at the moment. Also, we can connect and connect this with different kind of information. For example, we can use it for predicting that how much energy we need in the future. And this helps in the decision making and portfolio management. Also, it gives information that how much resources were used for producing the energy. So you know how to price it accordingly. So this is basically a mission critical information that we are providing here. There's some really nice features in the OPC UA data here. So like I already earlier said, that quality and status that are basically immediate feedback from the system. So if something in the source power plant goes wrong, then we immediately get some feedback in the quality bits of the data. Or we are just able to tell that, can we trust the data? Then we have separate timestamps, for example, the source and server data. So we are able to track different kind of delays in the system. And there is some requirement, for example, that we need the data to have within some time window. So we are able to track down the problems if we start to have lags in the system. And then there's different kind of events, which also, like if you add or remove measurement points into the system, you get automatic notifications. So OPC UA is really, really nice for this kind of features. In addition to the OPC UA, we basically implemented the performance monitoring. So we have a 24/7 monitoring system and network performance monitoring, which is constantly monitored. We have OPC UA endpoint communication is tracked all the time. So if some of the endpoints goes unresponsive, we get immediate notifications. We are following the data storage performance, for example, disk space or commits, how quickly they are done. Then the application performance, for example, CPU load or memory. And we have also the SMS and email-based alarms. So if we get problems, then those are immediately notified and we can start problem solving very fast. And with the OPC, we are able to, into alarm message, already give some initial indication of the problem source. So it's very, very good for debugging systems. And we were using the OPC UA, we were able to design a high availability. So we have multiple levels of redundancy. So we have OPC UA redundancy, application redundancy, database redundancy, and also network redundancy. So and there's no single point of failure in the system. So one component is always possible to crash without paralyzing the whole system. And this is where OPC UA is very, very much helping us. So summary is that with the OPC UA, we achieved a simple and future-proof architecture. And also this Business IoT ticket platform and OPC UA, they support each other in the best ways. And using these streamlined processes, we get clear responsibilities. And once we have the clear responsibilities, this always leads into a cost savings. And it also allows Helen to focus on the core business and value creation. Okay. I think I'm a little bit ahead of the schedule. On the other hand, we started a little bit late, so I think we could end today here. Before stopping, are there any questions now? Anyone in the meeting, would you like to ask anything about or return into some interesting slide for the discussion? If not, I think we could go into assignment. And I was thinking of free homework exercises that you could do. And it should actually be here. Let's change it a little bit. So I would like to think a little bit what are the key requirements needed in the, well, not only in the factory floor communications, but in the factories of the future communications, and how these key requirements, how they help achieving the cost savings. Second would be then, what is the publish subscribe pattern and where and how it could be used. And finally, figure out how a few examples how this IoT data could be utilized in the enterprise resource planning. So give some concrete examples of this. And kind of overall summary is that what I'm trying to provide in this course is basically ideas how to design this kind of systems. And OPC UA, there are other protocols of course also available, but when designing this kind of industrial systems, it's at least really good to understand that how different kind of challenges, how they are solved in the OPC UA. And then if you plan to use some other protocol, then you would be aware of the challenges and problems and how to tackle those with the different protocols. And gives a really good insight what must be taken into account in this kind of systems. And kind of I want to encourage digging deeper into OPC UA, and you can go search for the open source components, for example, and then start developing something yourself using those. Okay. Anything else? We are 4:10, and I think could stop here.
I will stop the recording here.
Okay, thank you. Thank you, everyone.
Thank you.